Now, I want to do an experiment, and the experiment that I want to do is I want to find out if nicotine patches work. So that's my question. Do nicotine patches work? And so let's assume that I get a big group of volunteers, people who all want to quit smoking. So I take this giant group of volunteers, and I want to randomize these volunteers, who of course are smokers who want to quit, and being a good statistician, I will randomize them into two different groups. Group number one is going to be a group that gets nicotine patches, and they will try to quit smoking. Group number two, this will be my control group. They do not get nicotine patches. And what I'd like to do at the end is compare the proportion that quit smoking in each group. Okay, so since we are comparing proportions, it doesn't really matter that the groups might not be the same size. And so in this example, I'm going to intentionally give you groups that are not the same size. So let's assume group number one has 143 people in it, and group number two has 151 people in it. Now, of course, these are not the same size groups, and that's fine that they aren't the same size groups. They don't have to be. And let's say in group number one, the number of successes we have is 46. So of the people who used that nicotine patch, 46 of those 143 were able to successfully quit smoking. Let's say group two, I only had 30 people out of my 151 who were able to successfully quit smoking. So whenever I find the proportion of people in group one who were able to quit, that turns out to be 32.2%. My proportion in group two, lower of course, 19.9% of people in group two were able to quit smoking. So whenever I ask the question, do nicotine patches work? The question that I'm really asking is, the people who took the nicotine patches, did they quit smoking at a higher rate than the people who did not take the nicotine patches? And on the surface, it seems like the answer is yes. It's a little bit more than 12% higher, 12.3% difference between the two of them. But the question is that high enough? 12.3% seems like a lot, but of course, in statistics, the way things seem can be deceiving. And so what we want to know is, okay, yes, 12.3% is higher, but is that statistically significant? Would we say that 12.3% is ridiculously higher, or is 12.3% within the realm of random variation? And so the way that we're going to do this is we're going to do a new type of hypothesis test. And the type of hypothesis test we're going to do is now going to involve two proportions. Previously, we'd only done one proportion, and we would compare one proportion to what we thought would happen. So it was what proportion we actually got compared to what proportion we expected to get. But here we're doing something a little different because we're comparing two proportions. How did this group do, and how did this group do, and how did they do in comparison to each other? Now, for the sake of argument and to save some time here, let's assume that all of the conditions for normal models have been met. Meaning I have at least 10 successes and 10 failures, they're random, they're independent. Let's assume the normal conditions are met just to save ourselves some time from having to check those. They're exactly the same as they are for a one proportion z-test, so we need to make sure we meet those conditions. And success and failure in particular is easy to check. I have at least 10 successes in the first group and at least 10 in the second group. And of course, I have at least 10 failures in the second group and at least 10 failures in the first group because everybody who's not a success is a failure. Notice I checked both groups for successes and failures. Both groups would need to be independent. Both groups would need to be random. Let's just assume that they are. Both groups meet the conditions. So let's write our hypotheses. Now, my null hypothesis, like all null hypotheses, is that whatever the treatment is that we're doing, whatever the thing that's going on, doesn't work. So the null hypothesis is going to be that the first group is equal to the second group, meaning there is no difference in the two proportions. You might also see this written as the first group minus the second group is equal to 0, meaning there is no difference in success between these two groups. The first group and the second group have exactly the same level of success. Our alternative hypothesis then is that it looks like the nicotine patches might work. It looks like it's a high percentage. So my alternative hypothesis is going to be that it does work. Again, there are two ways to write this. You could say that the first group has a higher proportion than the second group, or you might see it written occasionally like this. Now, I would say that the most useful way to write this, you certainly don't have to do both. They mean exactly the same, but I would say that this and this are maybe the most useful ways to write it. The reason I showed you both is because if you decide to use a graphing calculator, the graphing calculator will give you your hypotheses like this, comparing 1 and 2 directly across an equals or an inequality sign. But when we perform our z-test here in a minute, we need to know that the difference between them being 0 is what we are assuming happens. We are assuming there is no difference. So what should have happened in our z-test is going to end up being 0. And in fact, let's go ahead and get started on that with our z-score test. First of all, this is a 2-proportion z-test because we are comparing 2 proportions. And so our z-score is what did happen minus what should have happened over the standard deviation. So what did happen means what was actually the difference between the two? Well, the first group was 32.2% and the second group was 19.9%. So this is what the actual difference between the two was. And we expected the actual difference, according to our null hypothesis, we expected the difference to be 0. So the difference was 12.3%, but the difference should have been 0. Now here's the part where it's going to be new for us whenever we figure out the standard deviation. Now I drew a really big square root here because we're going to be adding two things together. We're going to be adding the standard deviation of the first group and the standard deviation of the second group together. Now the formulas for standard deviations are the same. It's still PQ over N. Still PQ over N, except we're going to have PQ over N for the first group, and then we're going to add PQ over N for the second group. So we're going to end up adding 2 together. Now before we fill in these numbers, we need to talk about what these numbers should be. Remember, whenever you do a hypothesis test, you assume that the null hypothesis is true. You assume that there is no difference between the two of these. What this means is that the proportion of success in the first problem and the proportion of success in the second problem should be exactly the same. If we are assuming that the null hypothesis is true, we are assuming there is no difference, these two should be exactly the same. But the question is, what should that be? It should be the same, but what should it be? And in order to figure out what it is, we do what is called pooling. And pooling is whenever you figure out what the proportion should be, the expected proportion, the predicted proportion, you figure out what it should be by taking the number of successes in the first group, which I told you was 46, and add the number of successes in the second group, which I told you was 30, and divide by the total number. In the first group, I told you there were 143, and in the second group, I told you there were 151. And when I combine these together to get one proportion, the proportion that I get is 0.259. So this is what I will use for my percentage chance of success. I combine the two together. And the reason that I combine the two together is because if the null hypothesis is true, and remember, when you do a hypothesis test, you assume the null hypothesis is true. If it is true, these two proportions, the first group and the second group, should be the same. So whenever I add them together, the proportion I get, this should be the proportion for the first group or the second group because I am assuming they're the same. Now notice, they are not the same. I know they're not the same based on my sample. But in a hypothesis test, I assume that the null hypothesis is true right up until I have reason to think it's not. So I'm assuming these two proportions are the same and that that same proportion is 25.9%. So when I go back and do the z-score, I get what did happen, which is going to be 12.3%, minus what should have happened, which is 0, over this standard deviation. Now I still need two of them because I still have two proportions, but the proportions are going to be the same. This is 0.259 is my p for the first group, and then the second group is going to be 0.741, and there were 143 in the first group. Plus, I need to write this a little longer, my second group, again, of course, I expect the percentages to be the same. I expect it to be 0.259 and 0.741, but the second group had 151 people in it. Now this, of course, is a really giant standard deviation here. So I got the P and Q by pooling my proportions, and I assume that it's 25.9% for both because I assume that the null hypothesis is true, and the null hypothesis says there is no difference between the two. I still kept the numbers different because the first group had 143 and the second group had 151. And if you're wondering why we're doing this, why we're just adding them underneath, what we're really doing is finding the variances and adding them. So for example, let me get a scratch piece of paper to show you why this works. One group would be PQ over N for the first one, and the second group would be PQ over N for the second group. And if I wanted to add these two standard deviations together, remember I'm not allowed to just add them together. What I am allowed to do is add the variances and square root. So I would square this and I would square this. What that does is it gets rid of the square root. So this is P1 Q1 over N1. This is P2 Q2 over N2. Now I have the variances because I squared them. Add the variances and then square root the answer. So that's what I'm doing. I'm finding the variances, adding the variances, and then square rooting them. That's what's happening right here. Okay? So I've already worked this out ahead of time, and the answer is 2.41. That is my z-score, 2.41. And so I want to know what is the probability that z is, do I want to know greater than or do I want to know less than for my z-score? So I come back to my null hypothesis. My null hypothesis was I want to know the probability of greater than. The probability the first one's greater than the second one, or the probability the difference is greater than 0. So this is an upper tail test. I want to know the probability that z is greater than 2.41, which on your z chart is 0.008. So if you draw the normal model, right here in the middle, this is 0 standard deviations, and I'm looking for this spot up here, which is where this upper tail, which is 2.41 standard deviations, and it turns out this probability is 0.008 right there. So what's my conclusion? Well, I would say that this p-value is low no matter which alpha you pick. Now we didn't specifically say what alpha was going to be, but I think it's fair to say like a 5% alpha would be reasonable. So if this is a 5% alpha value, what would our conclusion be? Well, our conclusion will be because my p-value is small, I reject the null hypothesis. A small p-value means reject the null. I reject the null hypothesis. There is strong evidence that, now what was there strong evidence of? Oh right, it was strong evidence that the first group was better than the second group. So there is strong evidence that wearing a nicotine patch can help a person quit smoking. Okay, so I did 2 of the 3 parts of a hypothesis test. I indicated that I was surprised, which is why I rejected the null hypothesis. I indicated how surprised I was. A p-value of 0.008 is certainly very low. That is unlikely to happen by random chance. Now let's talk about what would not surprise me by doing a confidence interval. So remember, the difference between the two in a confidence interval was actually 12.3%. This was the actual difference between the two. But let's go ahead and figure out the margin of error, and let's say a 95% confidence interval. 95% is a fairly common confidence interval. Now, just like before, I want to get the standard error, and I'm going to do it by combining the standard error of the first group and the standard error of the second group. So my standard error is going to equal PQ over N of the first one plus PQ over N of the second one. But remember, a confidence interval, I do not assume that the null is true. A confidence interval doesn't even have a null hypothesis. I don't assume the null is true. In a confidence interval, I use what actually happened. So when I come back over here, I see that the first group actually had a percentage of 32.2%. So I'm going to use that as my P, 32.2%. Which means my Q is going to be 67.8%, and that group had 143 people in it. Plus, my second group actually had 19.9% success. So my P here is 0.199, which means the Q will be 0.801, and that group had 151 people in it. And if I want to do a confidence interval, I will take my critical value, which will be 1.96, and multiply it by the standard error. I worked that out beforehand, and it turns out the entire confidence interval, 12.3% plus or minus the margin of error, is this. So there's where my confidence interval lies, between 2.3 and 22.3%. So what I can say is I am 95% confident that, no wait, hold on, what am I 95% confident of? Between 2 and 22%, what is that? What 2 and 22% are what? And remember, the difference of the proportions is where we got this. The difference between the two was 12.3%. So I think the difference is between 2.3 and 22.3%. Meaning I think using a nicotine patch can increase the percentage of people who quit smoking. How much could it increase it by? Well, somewhere between 2.3 and 22.3. So I'm 95% confident that the proportion of smokers who quit will be raised by between 2.3% and 22.3% by using a nicotine patch. Okay, so here's what we did in this problem. We performed an experiment in which we took two groups, nicotine patch and not a nicotine patch, compared those two percentages in a hypothesis test. Our null hypothesis was that the nicotine patch would not help, and our alternative was that a nicotine patch would help. We then performed a two-proportion z-test, which involved pooling our data to get the chance of success. The total number of successes in both groups, the total number of people in both groups, and that gave us the percentage chance of success. We used it twice for each proportion. The first group had 143 people, the second had 151. We found a z-score, looked up the z-score, and got our p-value. Our p-value was low, so in our conclusion we said our p-value is low, so we reject the null. There's evidence that the nicotine patch helps. Then we went ahead and did a confidence interval. The difference between the two was 12.3%. Here's the standard error for the difference between the two, which means our margin of error was between 2 and 22%. That's how much we expect a nicotine patch will raise the quitting rate by. That is not how many people or the percentage of people we expect to quit smoking. That's the percentage of people we expect to quit smoking higher than the average. Okay, that was a poor way of saying that. We expect a certain number of people to quit smoking anyway. But using a nicotine patch will help even more of them quit smoking than otherwise would have happened. How many more? Well, between 2 and 22% more people will quit smoking using a nicotine patch. And that is a two-proportion z-test.